ever just, stop and think about the biggest puzzles out there, like black holes or how everything even started with the Big Bang?
Oh, absolutely. They're properly mind-bending questions.
And when you really dig into the physics behind them, you hit this fundamental clash, don't you?
You really do. It's this fascinating problem we've had for ages. We've got Einstein's general relativity, brilliant for gravity, big stuff.
Yeah.
Planets, galaxies, the shape of space-time.
Right, the grand scale.
Exactly.
Yeah.
And then you have quantum mechanics, which is just fantastic for the super small scale. Atoms, particles, all that quantum fuzziness and probability stuff.
So it's like we know the rules for the forest and we know the rules for the trees, but how they connect, that's the tricky part.
That's a great way to put it. And, well, that's where this potentially groundbreaking new idea comes in from researchers at Aalto University in Finland.
Ah, okay.
Mikko Partanen and Chukka Tulkki. They've put forward a new quantum theory of gravity. They're, cautious about calling it a theory of everything.
Understandable. That's a big claim.
It is. But the goal is definitely to bridge that gap we were just talking about.
And this isn't just like abstract math for its own sake, right? The sources mentioned GPS. We use tech based on Einstein's ideas every day.
Absolutely. That's a perfect example. Understanding fundamental physics, even the really abstract stuff, eventually filters down. So imagine if we could actually unite gravity with the other forces.
Now, what could that mean? Better understanding, maybe even new technologies down the line.
That's the hope. Think about those extreme places inside black holes, the universe's first moments. Places where gravity is immense and quantum effects matter. Our current theories just, they sort of give up there.
They break down.
They break down. So our mission today for this deep dive is really to unpack what this new Aalto theory is about, why it's causing a stir, and, what its potential implications might be.
Okay, let's get into it. The core problem, this incompatibility. Can we flesh that out a bit more? What exactly doesn't fit?
Right. So the big issue is that gravity, as Einstein described it, just doesn't mesh with what we call the standard model of particle physics.
Okay, the standard model.
Think of the standard model as like our best rule book for almost everything except gravity. It covers the electromagnetic force, light, magnets, electricity.
Got it.
The weak nuclear force, which is involved in certain kinds of radioactivity, and the strong nuclear force, the glue holding atomic nuclei together. It works incredibly well for those three.
But gravity's just left out.
Completely left out. The forces in the standard model are what physicists call gauge theories. This is kind of important.
Gauge theory.
Yeah, they come from deep mathematical symmetries, and they have associated messenger particles. Like the photon carries the electromagnetic force.
Okay, like little messengers passing the force between particles.
Exactly. But gravity and general relativity, it's described totally differently. It's about the geometry of space-time itself, bending and warping because of mass and energy, not particles carrying a force in the same way.
So fundamentally different descriptions. Apples and oranges.
Pretty much. And that's the hurdle.
Okay, so Partanen and Tulkki arrived with this new proposal. How are they trying to bring gravity into the fold, make it play nice with the standard model?
Well, their central idea is to formulate a quantum theory of gravity that is, by design, compatible with the standard model. And they do this by proposing a gravity gauge theory.
A gravity gauge theory. Okay, let's break that down. What does that actually mean in practice?
Remember how we said the other forces have messenger particles?
Yeah, like the photon.
So the idea here is analogous. Think about how particles with electric charge interact via the electromagnetic field, swapping photons.
Right.
Their theory suggests that particles with energy interact through a gravitational field, potentially with its own kind of messenger interaction, fitting that gauge theory structure.
Ah, so energy is kind of playing the role charge plays in electromagnetism. Is that too simple?
It's in that ballpark, yeah. But this really clever bit, the core innovation, is about symmetry. The standard model forces all arise from these internal symmetries of particles.
Okay.
General relativity is based on a different kind of symmetry. Symmetry of space-time itself, the fact that the laws of physics are the same everywhere. This new theory tries to find a symmetry for gravity that looks more like the particle symmetries in the standard model. That's the big shift.
That does sound like a completely different angle. Why is that approach seen as so significant? I mean, why haven't people just managed to quantize general relativity directly?
People have tried for decades. The fundamental issue is that clash of descriptions we mentioned. General relativity gives you this smooth, continuous space-time fabric.
Like a trampoline bending.
Sort of, yeah. But quantum field theory, the basis of the standard model, is all about discrete chunks. quantum particles interacting probabilistically in fields. Trying to mash those two mathematical frameworks together just leads to, well, mathematical headaches. Infinities pop up everywhere you don't want them.
So it's like trying to use incompatible tools for the same job.
Exactly. And we really need a quantum theory of gravity for those extreme situations. Black holes, singularities, points of supposedly infinite density, the Big Bang itself. Our current physics just can't describe the physics at those points.
They hit a wall.
A hard wall. The source mentioned Partinen was driven by these big questions from early on, and this symmetry idea was key. He then worked with Toki to build it into a proper mathematical framework.
Right, taking that core insight and developing the full theory.
Developing the quantum field theory for gravity based on that symmetry principle.
And if they're right, or even on the right track, what are the potential payoffs? The source mentions some pretty huge possibilities.
Oh, absolutely huge. Partinen himself said, and I'm quoting here, if this turns out to lead to a complete quantum field theory of gravity, then eventually it will give answers to the very difficult problems of understanding singularities in black holes and the Big Bang.
Wow. Understanding the origin of the universe and the insides of black holes, that's profound.
Isn't it? And he also mentioned it could shed light on other big cosmic mysteries, like why is there so much more matter than antimatter? Why do we exist at all, basically?
Okay, that's incredibly ambitious. But, as you said, they're cautious. It's not proven yet. There's still a big test it needs to pass.
That's right. The theory is out there, but it's undergoing intense scrutiny. And the crucial step, the make-or-break test, involves something called renormalization.
Renormalization. Okay, sounds technical. Can you simplify that for us? What is it and why is it vital here?
Yeah, it's a bit math-heavy, but the basic idea is this. In quantum field theories, when you're actually trying to calculate things like the probability of particles interacting, you often run into calculations that spit out infinity as the answer.
Which isn't very helpful. Infinity isn't a physical measurement.
Exactly. It usually means something is wrong or incomplete in the calculation or the theory itself. Renormalization is a set of mathematical techniques developed over decades to carefully subtract out these infinities in a consistent way, leaving you with finite, meaningful, predictable numbers.
So it's like a mathematical toolkit to tame the infinities.
That's a good way to think about it. Now, Partinen and Toki have shown their theory can be renormalized for the simplest kinds of interactions, what physicists call first-order calculations.
Okay, so far so good.
Right. But here's the catch. As Toki puts it, if renormalization doesn't work for higher-order terms, you'll get infinite results. So it's vital to show that this renormalization continues to work.
Yeah.
They need to prove it works for all levels of complexity in the calculations.
So it needs to be consistently fixable, not just fixable for the easy cases. If infinities pop up again in more complicated calculations and can't be removed,
Then the theory, as it stands, wouldn't be predictive. It wouldn't be a complete physical theory. That's the critical test they're working on now.
it sounds make or break. But they seem hopeful.
They do. Parton mentioned, I can't say when, but I can say we'll know much more about that in a few years. So they're actively working on this proof and seem optimistic they can achieve it.
And they're not doing this in isolation, are they? They've published it.
Absolutely. That's crucial for science. Their work is published in reports on progress in physics. This means other physicists worldwide can look at it, challenge it, test it, try to verify the results, maybe even build on it.
Open it up to the community.
Exactly. Partinen explicitly said they hope it will open countless avenues for scientists to explore, comparing its potential impact to how quantum mechanics and relativity opened up whole new fields of physics.
So let's just recap the key points for everyone listening. We have a fundamentally new approach to quantum gravity coming out of Aalto University.
Right, based on gauge theory principles.
Designed specifically to fit with the standard model, not replace it entirely, by treating gravity using similar ideas of symmetry and field interactions.
Using energy somewhat like charge and aiming for a particle-like symmetry.
And the potential payoff is huge, maybe explaining black hole singularities, the Big Bang, perhaps even the matter-antimatter asymmetry.
Really fundamental questions.
But the big if right now hangs on proving this mathematical technique, renormalization, works consistently for the theory.
That's the crucial next step.
Yeah.
Proving the math holds up under pressure.
Okay. It really underscores that science is a process, isn't it? This is a potentially massive leap. but it needs that rigorous validation.
Absolutely. It's a bold, exciting idea, and even if it needs refinement, it offers a genuinely new direction. That in itself is valuable.
It really is. And it just gets you thinking again about that connection between fundamental physics and the real world. Like the GPS example.
Yeah.
Understanding gravity seems so abstract, but it led to technology we rely on. So if this new theory or something like it proves successful, what comes next?
What unforeseen applications might appear decades down the line?
Exactly. Or even what new questions will it force us to ask? Questions we can't even imagine right now.
That's always the most exciting part of fundamental breakthroughs, isn't it?
Yeah.
The journey continues, and this work from Partinen and Tulke is definitely a fascinating chapter in that ongoing story of discovery.